Hello everyone, welcome to this video about integration by parts. Just remember that the integration by parts formula is integral u dv is equal to u times v minus integral v du. Now what I'd like to do is actually use an example to follow up from class today. We'll look at the integral of x cubed times ln of x dx. There are various choices that you could use for u if you're going to do integration by parts. Just keep in mind that integration by parts is different from u substitution. So even though a u is being used, they're different things. For instance, u equals x would never be useful in substitution. It would waste time. I mean, just try it once. But it is sometimes an okay substitution in integration by parts. Now, what are the various choices for u which might make sense for this integral right here? Well, maybe u equals x, maybe u equals x squared, maybe u is equal to x cubed, and I think that's all you can get away with if you decide not to use ln of x. But some choices using ln of x, well, maybe just ln of x, maybe just u is equal to ln of x, maybe just u is equal to x ln x. Then how about with one more power of x, so maybe u is equal to x squared ln x, and maybe the whole thing, right? Maybe u is equal to x cubed ln x. And barring something weird, those are probably the only choices. One of these things are the only ones that are going to probably work for u. And it takes some ingenuity to figure out what you need to do. After some practice, you'll see that maybe this isn't really the one. So let's see what happens by using u is equal to x cubed. Okay, and this might work and this might not work out, but this is kind of how these things go, and you have to feel these things out, and you have to practice a million of these to figure out really what's going on and to build some strategy and intuition. So let's try u is equal to x cubed. So that is all of this stuff right there, and that will account for the u right here. And that actually means, in order, if you look at the formula right up here, dv, I'm highlighting this in magenta, that's got to be all the rest of this stuff. So this is automatic. So dv now has to be equal to ln x dx. Okay, there's no choice. So once you pick u, dv is automatically everything else that's in this integral. And now the point is that the integral we were given is the entire left side of the integral, so including the integral sign. It's the entire thing. And now this formula says, okay, replace this with all this stuff over here, but look what it calls for. This formula calls for a v. We don't have v, we have dv, and the formula also calls for a du. We don't have du, we just have u. So first we have to compute those things. So the derivative is not too bad. In fact, the derivative is supposed to never be bad. You might be still a little rusty on differentiation, but you have to get rid of that quickly. In this class, the differentiation must be automatic. I mean, you have to just know the chain rule and all that stuff. Using the chain rule, you can differentiate just practically anything. And the real tricky thing always in this class will be the integration. So for instance, right here, you have to integrate ln of x. We actually did this in class on Thursday. What do you do here? You really want to write for v. You want to write whatever ln of x integrates to, and we did this. We actually looked at, if you'll remember back in your notes, you'll see integral of ln of x dx, and how we did this was we did an integration by parts. Okay? So there's this one integral you have to do right here, and when you do this, if you look back in your notes, you'll see that you have gotten that v, the antiderivative of ln of x is x ln of x minus x. Okay, so this step, I mean, there's quite a bit of work here. It's its own integration by parts problem, and we won't show that. But now the whole point is this integral right here, instead of working with this, we replace it due to the formula with u times v. So that's u, which is sorry, I didn't actually want to write that. Let's try this again. U, which is x cubed, okay, times v, So let's try times v, which is right there. Now, because v has a minus sign in it, we better really put this in a set of parentheses, right? X ln x minus x. Okay, copy the minus sign in the formula here, then integral v, then du. So this thing here times this thing. Now, again, because we're multiplying these two and v has a minus sign, we better use a set of parentheses. Okay, so there's v in parentheses, and then u is 3x squared dx. Now, whatever u times v is, you really don't care, because there's no integral in front of uv, so it doesn't matter what it looks like. You never really care about that. It's never going to cause a problem. It's this integral, right? So you have two integrals to do, just to recall again, right? So here's one integral. This step right there is an integral. And then you have this final integral that you have to do. Well, here, a product is you can't just split this up how you want to, but you could at least distribute this 3x squared. And then you have, when you do that, you actually get one easy integral, right? You'll have to integrate 3x squared times x, so that's just 3x cubed. That integral is not so bad, but then you have the integral of 3x squared times x ln x. And that is actually going to end up being a mess, right? So in fact, if you look at it, it's, ignore the 3, but you have x cubed ln x, and that's basically the same thing you had before. So this choice of u seems to not really work. So the whole point now is we're just going to undo all of this. Okay, this ended up not being a useful choice for u, so we're going to just say, let's just kind of get rid of all this stuff. Alright, so I did that pretty quickly, but now this choice didn't work out. And you can actually, go through and check, and you'll see that these don't end up producing good results either. Maybe it's going to be this one, or maybe it's going to be this one. So let's see what happens by using u is equal to ln of x. So u equals ln of x. That is, what is that? So this u is going to be that. Now, everything else that appears here, right, has to be dv. So everything else that's here, so that this integral is this entire side. So dv will be x cubed dx. Do not forget the dx, okay? So dv is x cubed dx. So by using u is equal to ln x and dv equals x cubed times dx, you can now see, again, like before, that the entire integral over here, everything here, is accounted for. Okay, so now let's take the derivative of ln of x. Okay, that's not so bad. Right, this is du is 1 over x. Don't forget the dx here. The point is you see a dx sort of in the diagonal along here. And then finally, here we have to integrate. So v is going to be x to the 4th over 4. So this was not a bad integral to do, right? Because you just had a polynomial. So often what you'll try to do is you'll pick u to be everything other than the part that's a polynomial, because that was an easy integration. So now let's piece together what the integration by parts formula says to do. This integral right here, okay, this integral is equal to u, there's that u right there, okay, so u, which is ln of x, times v, which is x to the 4th over 4. I don't want it to get mistaken as an input to ln, so maybe I'll throw in a set of parentheses. Again, this looks a little weird, but hey, we never have to integrate this thing. There's no integral sign right up here, so we're great. Copy a minus sign, then integral v, which is x to the 4th over 4, then du, which is right here, it's so we have times 1 over x dx. Okay, this looks pretty good. This is going to be x to the 4th over 4 ln x. By switching the order, now I can drop all these parentheses. There's no confusion. Maybe bring this 4 in the denominator out. So you have 1/4 integral, and you have x to the 4th divided by x. That's got to be x cubed using some algebra. And now we can really finish this off. This is a nice integral, right? You have x to the 4th over 4 ln of x minus a 4th times, and when you integrate x cubed, you have x to the 4th over 4 and plus c. So the point is, this entire expression is this one, which we simplified to this final line right here. And this thing, namely this underlined thing, is equal to the original thing. We were asked about this, and we replaced it with this, which was eventually this. The key thing to note, really, in all of this is that when you do integration by parts, this was successful, but right here, this is an integration step, okay? And then right over here, you set up a new integral, and so you had, we did it over here after simplifying, but there's another integral. So there's one integral over here, there's a second integral over here, and each of these two integrals, you need to solve either using basic integration techniques, meaning using no u substitution at all. You just have to recognize, aha, the derivative of some function is the function listed here or the function listed there. Or you might have to do u substitution on that integral. Or you might have to do an integration by parts. Even though you're in the middle of integration by parts problem, doing this integral or doing this integral might on its own require integration by parts. And actually later in this class, you will be learning other techniques outside of section 7.1, for instance in 7.2, 7.3, and 7.4, and the list of ways you might have to do this integral might grow. So really the whole point is these are the old techniques from 207, and you really need to be as sharp on those so that when you see this setup, what Dr. Kim thinks is going to be a doable integral over here might be different than your notion of what integral you can do. So if I set up something for you and I see dv and I think, oh wow, this thing is impossible to integrate, it really better be impossible, and you have to see that quickly so then you can move on to a different choice for you. And the whole point is, this u worked out for us here, but if none of these u's work out, then really for this problem, integration by parts won't be the technique and you'll have to move on to something else.